The following program is brought to you by Caltech.
Okay, our next speaker is Damon Landau from JPL. Damon is an outer planet mission analyst at JPL and specializes in mission design and trajectory optimization. Before venturing to sunny California, he earned a PhD at Purdue studying strategies for the sustained human exploration of Mars. He has participated in numerous small body studies and proposals seeking targets for anything between small robots to large spaceships. So please welcome Damon Landau.
Thanks for the introduction, John. Hi, everyone. I'm Damon. And I am going to talk a little bit about the trajectory design for solar electric propulsion missions. And the fun thing about doing SEP trajectories is they're really tied into the spacecraft. So the mission design systems type stuff is really tied in there, which means that you get to meet a lot more of your colleagues while working on these things. And I'll talk about how we sort of try to use this technology to go out and steal a stone from the heavens. So here's a screenshot from, it's actually a thing I saw on YouTube for all the asteroids that are being found. So this is when Neowise was spraying out along the track of Earth. Okay, so earlier on this morning, I hear that John told had a talk about giving an overview of the mission. So, so sort of from the trajectory and design side, this is how we came up with our proof of concept. So we wanted to look at what it would take to return a 10-ton asteroid down to the space station, actually. So has a proxy for a 10-ton asteroid, because we don't really have any of those known quite yet. We used an old favorite, 1991 VG, which has an orbit very similar to Earth. So I basically just wanted to use an actual trajectory with a fake target, I guess. So I have the mission phases broken down, and then the rest of the talk will sort of go into each of these into more detail, but I'll just sort of try to give an idea about how these different things affect the actual design. So the first thing is, if we're trying to return a 10-ton object, it's going to take a lot of propellant to move that thing around. So with launch, we're looking at launch with a 10 to 15-ton spacecraft. About 5 or 6 tons dry mass is what it ended up being, but we might be able to work that down, I'm not sure. And about 8 tons of xenon, plus or minus, depending on how big of a target you want and what sort of trajectory you want. So in order to get this type of mass, you can either launch directly into low Earth orbit, and with that you can use a mid-class Atlas V to do that, or you could launch up to a geo transfer orbit, and in that case you need a bigger rocket. So we use the Delta IV Heavy for that design. And then the time frame for the launches, we wanted to look at launching somewhere in the mid to late teens, so that we could get back to the space station in the early 2020s, when we're still assuming it'll be still upkept. So following launch, if we launch to low Earth orbit, then we have to spiral up. And the departure spiral, the time on that spiral is determined by the how powerful the solar electric propulsion is. So we looked at a 40 kilowatt system in order to try to get reasonable flight times. We wanted the flight times to be between 5, 6 years in that time frame. So to spiral up from low Earth orbit takes about 6.5 kilometers per second and about a year and a half. However, if you spiral from geotransfer orbit, you can shave a year off the flight time, which is basically telling you what the investment in buying the bigger rocket is. If you want to save a year off your flight time, go with the larger rocket. So that gives you the trade between those guys. And so that's basically just this part here where we launched. So we launched to low Earth orbit. The mass with the 521 was about 14 tons. And then we spiral up, and then that 6.5 kilometers per second took off almost 3 tons of xenon in order to get our spacecraft up. And so we spiral it up to an orbit that intercepts the moon with a relatively high V infinity for the moon. The V infinity with respect to the moon, we want it to be about the same as the orbital speed, so about 1 kilometer per second. And using that, we can actually do a gravity assist or two of the moon, and we essentially get 2 to 3 kilometers per second of delta V for free by having the moon eject us out into interplanetary space. So that's here where we depart Earth. And so you see we depart, and then we don't have to thrust so much because we already have a little bit of speed coming out, and then the electric propulsion system turns on, and then this is the thrusting to rendezvous with the target. So that's the sort of interplanetary trajectory portion, and that since we sort of limited ourselves to targets that already had orbits very similar to Earth, the delta V on that was relatively low. So on this part, particularly when it's closer to 1, but if you go to more demanding targets, it can go up to 4 kilometers per second, and the flight time can be 1.5 to 3 years. So we rendezvous with the target, stay there for 90 days. I think we depart here, start thrusting again, do a loop, and then we and then arrive back at Earth here. And again, we can do the same trick that we used to escape. We can use the moon to capture us. And so here we basically have to alter this arrival time such that the moon is sort of at the right phase to capture us into orbit, which is why we can arrive with a non-zero V infinity. This corresponds to a C3 of 2. And then, so you see, during the stay time, our mass went from about 11 tons up to 21 tons. So that's picking up the 10-ton object. So now we have a much heavier spacecraft. So the spiral time, when we go from our capture orbit down to the International Space Station, takes over two years to do that now. But this is how we sort of try to get everything into the box of being able to launch on existing rockets and do it in a reasonable amount of time. Okay, so after launch, the first thing that we do is the SEP Spiral, and there are trades that we can do with this. So on the bottom here, going across the bottom, we have the specific impulse of the system, and then going up and down, we have the solar array power scaled to the mass of the spacecraft. So here, this is for the SEP Spiral out. So you start with so many tons in low Earth orbit. So if you have 13 tons in low Earth orbit and a 40 kilowatt system, then the ratio there is, you have 3 kilowatts per every ton in low Earth orbit. And we see that as the specific impulse goes up, that is, as we get more efficient in terms of the propulsion system, the ratio of what we launch into low Earth orbit to what actually gets up to high Earth orbit keeps increasing. And we can get very, very high payload rate ratios. So here this line is 75% of whatever we launch into orbit ends up being usable payload. However, for a fixed power, so if we fix it at 3, as the specific impulse goes up, the thrust goes down, which means that it takes longer. So we don't want to push the ISP all the way up to the highest thing, because then we get into spiral times that take a bit too long. And this is, these plots are sort of how we came to zone in more on a 40 kilowatt system, because if we have a 10-ton object that we're returning and the spacecraft mass is about 10 tons, then we have a 20-ton spacecraft and a 40-ton object, and if our ISP that we're getting out of the Hall thrusters, which I think John also talked about, is between 2,000 and 3,000 seconds, then we can do spiral times of about 2 years, maybe a little bit more. However, if we have a 100-ton object that we want to bring back in a 20-ton spacecraft, then we have something like a third SEP power rate, and so there the spiral times just start to get increasingly longer as we go down. It's sort of an inverse relationship between power and time. This is sort of how we're getting from these orbits that are just on the edge of Earth, just captured into down to low Earth orbit. However, we can trade that for geotransfer orbit and sort of remake these contours with some relatively simple equations. And then we'll probably have to add some margin to account for radiation going through the belts and shattering. But again, that's also a function of what sort of spiral orbit you want to do. Some orbits are better than others. So that's something that can also be traded. Okay, so that gets us from near the Earth to out to the edge of Earth, and then the lunar gravity assists are what get us from the edge of Earth out into interplanetary space. So here, this is a trajectory plot of capturing. So here we're arriving back at Earth, and the energy relative to Earth is about 2 kilometers per second squared. So we come in and we do a flyby of the moon, and then from that flyby, we can go into any number of different orbits. So here, as an example, I go into a 3-to-1 resonant orbit with the moon, and this is just a conic. So the sun will actually perturb this, but this also gives an idea of this type of energy might be something that you can get onto a multi-body manifold, and Marco will talk a little bit more about those next. So we can basically use the moon to capture into the Earth system. From there, we can do more flybys of the moon if we want to get into a tighter orbit. So this is a one-to-one resonance with the Earth. So here are how the lunar flybys are altering the energy of the orbit, basically the size of the orbit, but we can also change the orientation of it. So here we're coming in, and so here the moon's inclined to Earth, the equator's sort of like this. We go into the moon, capture into this orbit, do another flyby, we can get into this other orbit. So we can basically use the moon to push around where this object is and where we might want to keep it. So that was just one example. And then when you go through all the combinations of what you can get a sort of map of how you come into the Earth-Moon system affects how you can get captured. So these plots give us basically the capture C3 are the colors versus the direction that you come in. So this is the right ascension of where you're coming in. So, and this is the declination actually to the ecliptic. So you do see that sort of 5-degree inclination of the moon sort of skews this a little bit. But we see if we want to do just lunar flyby and capture into a 1-month period orbit, we have a pretty wide range of declinations that we can get in and still have a C3 of around 2. We can actually get up to 2.5 in certain parts of the lunar orbit. So the reason that there's a variation off here is mostly due to the eccentricity of the moon. It's easier to capture when the moon's at perigee. So what you're able to do literally does depend on the phase of the moon at the time. So this is capture into a tighter orbit. If we want to capture into a more loose orbit and then maybe go off into 3-body land for a little while, then we can get up to much higher energies coming back. So we can get up to C3 of about 3 coming back. And so basically what that means is that the solar electric propulsion system has to do less work because we're getting more work out from the moon. Okay, so here are some more interplanetary trajectories. So we had a sort of proof of concept on the first slide, but we can also look at what happens if we want to alter the launch years, if we want to give like a primary mission and a backup, sort of how things are affected that way. So here's a trajectory. This is actually different than the one on the first slide. So here the Earth's in blue, the asteroid is in gray to sort of make out here. Then the trajectory is black with old gold thrusting, showing you when the thrusters are actually on. And so here I'm just giving data for the interplanetary portion because we can sort of decouple all these problems to make the design process a little bit easier. So here it's taking 2.5 years from Earth departure. Go do a little bit of thrusting, rendezvous, hang out for a little bit on the asteroid, come out and arrive back at Earth. And so here it only took less than a ton of xenon just for the interplanetary portion. But if we wanted to push back a year and so try to get different launch opportunities for the same flight time, we actually require about a ton more xenon. So in that case, we might want to over-design the tanks to be able to fill up more xenon, and actually and that would also up the mass, the wet mass of the spacecraft, which means we'd also have to go up to a slightly larger launch vehicle. However, this could be an effective way of being able to get some robustness into the overall mission design. So here we say it's not too bad between these two, and again, this is with 1991 VG. However, we can also look at what happens if we want to look at targets that aren't necessarily in the most convenient location at the time. So here's the 1991 VG trajectory again. So this is one where it's a target that's sort of in phase with Earth. The close approach to Earth is in the same time frame that we're wanting to do the mission. So this one has a close approach in 2017 to Earth, and we're actually arriving at the asteroid and departing in 2017. So in this case, we were able to get by with a relatively short flight time mission, less than two years from Earth departure to Earth capture. We used less than a ton of xenon. However, if we look at another target, which is wholly out of phase when we're looking at what we're going to do. So this is with 2006 RH20, which also has an orbit very similar to Earth. However, around 2017, it's on the opposite side of the Sun, which means that from the departure of Earth, we have to go into these sort of phasing loops to alter the period until we can catch up with the target, rendezvous with the target for a while, and then depart, and then we have to do another phasing loop back. And those phasing loops, you can buy them with additional flight time, but it adds a year or two outbound and inbound in order to make that happen. The other thing is it also took more xenon in order to do that, because we're essentially doing more delta V on the trajectory in order to basically to solve the phasing problem. We have to change the period and then change it back in order to get back to Earth. So it is sort of possible to get targets that aren't necessarily convenient at the time, but you buy it with flight time and in a reasonable amount of propellant. Then there's the other option, which John asked me to do a couple weeks ago now, I guess. Let's look what happens if we capture into a loose orbit and don't worry about spiraling the thing all the way down to the space station. So I mentioned before that the main driver for the SEP stage was how long it takes to actually spiral the large object from captured at Earth down to the space station. So here again we have 1991 VG launching in a time frame that's where it's near where it's near the close approach. Here we have 3.6 years for the interplanetary and 3 tons of xenon. However, we don't have to. We took off the extra two years spiral, and we have an extra 4 tons of xenon to play around with to push around this thing. So in this case, we depart Earth, chug along, rendezvous with the asteroid, pick it up, and then bring it back to Earth. In this case, we're looking at a 500-ton object that we're able to work with now, which is actually getting up to the mass that sort of corresponds with the size of objects that we actually have that we know about. So this one has an absolute magnitude of about 28.5, which corresponds to a diameter of around 8 meters. This is assuming a 15% albedo, so it can be off by a factor of 2 either way, depending on which part of an asteroid it was chunked off of. And then we also have the orbit condition code, which gives us an idea of about how well we actually know where this thing is. So condition codes of 0, 1 are good. We have a good idea where it's at. 2 and 3 is a little bit more off, but should be doable. And then things higher than that might need to look more into what it actually take to recover it. So here's one where it lines up where it actually wants to arrive back at Earth corresponding to when that close approach is. And so basically what we find there is because the asteroid is already naturally coming close to Earth to begin with, you just give it a small nudge a year or so before you want to go, or before you want to return it, and then it works. However, what that also means is that the variation that we saw, jumping launch years sort of goes away, because if we push it back a year when we arrive at Earth, instead of the asteroid, naturally wanting to be, sort of around here, it's going to be over here somewhere or something like that. And so the same trick, looking again at 2006 RH20, which is again totally out of phase during the launch time that we want. We still go out, and in 6 years and spend about five tons of xenon, bring back a decent sized object, but instead of bringing 500 tons, you only bring 50 tons back to Earth. So it makes it more hard when the thing's totally out of phase. But we do have a handful of objects that we know about that are sort of in this several meter across regime. And so looking at a couple of them, looked at where the closest approaches are. So here we're again looking at returning 500 tons to orbit. So here's 2007 UN-12, which has a close approach wherever our arrival is, so in 2020. So this one departs Earth in March of 2017. If we're doing a 1.5-year spiral before that, then that puts actual launch into late 2015. But this object's only 6 meters across, so this 6 meters to this 500 tons might be a reasonable match. The orbit condition code is a little bit higher, so the orbit might be a little bit off. So instead of arriving in October, might actually want to arrive in November or something like that. But we have another object where we can launch later. That object is 2009 DD. You guys can see it better than me. And so with this one, we're taking 4.5 years after escape. So that's like a 6-year total mission using 5 tons interplanetary. This is a 7-meter across object, and we have a decent idea of where it is. So this is a nice one that sort of fits all the parameters that we're looking at for actually trying to go out and steal an asteroid. So again, if we put ourselves in a box that we think sort of technically doable, a 40 kilowatt SEP system, a lot of xenon, but I think we talked about how Hall thrusters can do a lot of throughput and not taking too long. We can return 10-ton objects to the space station, or we can return 500-ton asteroids into a captured orbit. And then once it's in that captured orbit, there are options of what to do with it, which we'll hear about from Marco next. And so if you fix the trajectory, then the power and the spacecraft mass will scale with the asteroid mass. So if we instead want to do a 20-ton asteroid, then we really need to double everything. So we need a 80 kilowatt system. Conversely, if we keep the same object and keep and up the power, we can sort of cut down on the flight time on the spirals, which are a big chunk of the actual total flight time of the mission. And then the interplanetary trajectories, they don't really change in terms of flight time so continuously. They sort of want to come in more 1-year chunks, corresponding to the number of revs that you do from departure to arrival. The best time to go or to bring the thing back to Earth is when it already wants to come near Earth. We just sort of nudge it a little bit closer and do some targeting with the SEP system to do the lunar flyby to capture. However, if you have a big honkin' asteroid, it might be expensive in terms of propellant and flight time to alter when it actually arrives. And that's all I got. I'll be happy to entertain questions.